Come to be? That's the question. This is all scientific theory. Okay. It started with dust and gas. This is a very large nebula. Something really cool about these nebulas are that, excuse me. Here's an emission nebula, an absorption nebula. We've all seen the horse egg before. These nebulas, the density. What happened? What is the deal? Okay. The density of these nebulas is less than cigarette smoke for the most part, which is pretty amazing to me. You know, you look at them through your telescope, the Orion Nebula, I always think of a bunch of cotton balls or something about that thickness, but really, if that nebula were sitting in this room, we wouldn't even know it. We could be sitting inside right now and not even see it. It's so big. So these nebulas are everywhere. This is the Cygnus loop. It'd be pretty tough to see that through your telescope like that, but you probably could with a good camera. Yeah. I mean, I smoke all the time through my telescope and I don't see any of it. So anyway, these nebulas are made up of heavy elements, carbon, oxygen, nitrogen. Basically everything that we're made of and everything we know is made of is floating around in space in these nebulae. And that's where everything comes from, the compressing the stars, the planets, and us. This is a molecular cloud made out of beer, basically. It was in the news last year. It's ethyl alcohol. NASA publicized it as being made out of beer to get more people interested in astronomy. You know, it worked. I drank some of this cloud recently. So. It's a little bit higher density. We're going to have to put up our call. It's a little higher density than the other ones because it's made up of heavier elements. And these elements float around in the universe forever. They're all over the place, everywhere you look. They're just waiting for something to cause them to compress into a star. Then you got to have something to trigger that compression, like a nearby supernova. Anybody recognize this? Anybody else recognize this? Crab. Okay. The Crab Nebula, seen by Chinese and Europeans in the what, 1600s or so? 1066 or something. This supernova is an exploding star that causes shock waves all around it. Okay, and these shock waves affect everything around them, you know, thousands and thousands of light years. In 1987, this star became this star overnight, and that's in the large magnetic clouds that is on the southern hemisphere. Brighter than the entire galaxy for several days, so that's how strong the supernovae are. These supernovae explode violently, and they push out all these heavy elements into the universe, which are eventually turned into me and Art Zorka and Steve Beer. That's where they all come from, according to science, okay? So sometimes a passing star or even a shock wave from some smaller explosion they'll cause these nebulas to have a little bit of pressure put on them, or a rotation, or possibly a compression. Any tiny, remember you're dealing with something 1,000th the density of cigarette smoke. So in my living room I tested this out. If you blow cigarette smoke and then you just go like that about 20 feet away, you can see the effects of it all through the cloud. So you can see how it would compress this gas. So all you need is a trigger. You get gravitational collapse because these things are attracted to each other even in their smallness. They're still attracted by gravitation. This is an image from Hubble of a bunch of dense gas clouds. I say dense, they're not very dense, but they're dense compared to the vacuum of space. They compress into smaller objects like here, and here, and here, and here, and here. They're compressing for whatever reason, and as they compress, here's the good old Orion Nebula through my Canon 40D. This one is supposedly filled all up with stars compressing. And something about, for you people that haven't taken this picture yet, all of us take this when we get our first telescopes, and this is like the coolest thing in the world. This part is just dark, and it's in front of that part. There's nothing different about it. Inside the Orion Nebula, these are Hubble images of protostars that have compressed due to gravity into small spheres of rotating debris. Okay? And this contains all the molecular molecules and atoms and everything else that were in these nebulae to begin with. They compress into these small protostar type deals. They begin to rotate. I don't know if anybody saw on the space shuttle where the guy put the grains of salt into the bag and shook them up and washed them. They attracted each other because of electrostatic attraction, and this guy discovered something really important by shaking some salt in a Ziploc bag on a space shuttle. It was one of the most profound discoveries. It changed the whole theory of planet forms. But that's what happened. So the nebula collapses due to gravity, and of course when you increase pressure on a closed system, the temperature goes up. So as these things compress and compress over millions of years, the temperature gets hot enough, around 25 million degrees Fahrenheit, supposedly, that hydrogen atoms start to fuse together in a complicated process, which unfortunately we'll get into in a minute. But they fuse together and form helium, and they release energy in that process. Some of the mass is converted to energy, according to a famous equation that any of you amateurs know, because I'm certainly an amateur.
E equals MC squared.
Right, E equals MC squared. It's not just a cool song by Big Audio Dynamite. It's also an equation. What exactly is the sun? Well, we're talking about it now. This is 4 images from the SOHO probe. SOHO stands for Solar Heliospheric Observatory, and I bored everybody to death with about an hour's worth of information on that last time, so I won't go through that again. But just imagine a big school bus with 4 of my telescopes strapped to it floating around in outer space, and it's taking images all the time. This is ultraviolet, and these are just different wavelengths of light coming from SOHO at the same event. So it's a pretty active object. A nice big prominence there. The Earth is about the size of this red beam up there. That gives you the scale. So again, 75% hydrogen, a little more than 24% helium. Less than 1% of it is heavier elements created by fusion or in the original nebula and still in the sun. Interestingly enough, when you say 75% hydrogen, we're talking about, well, the number of atoms is totally different. There's 91% if you count the number of atoms, but of course hydrogen atoms are much lighter than helium atoms. So if somebody really wanted to squash the numbers, this is the percentage of total number of atoms in the sun. Okay, 91% hydrogen, 8% helium. So you can see the sun's got a whole bunch of hydrogen left over. So it's not going anywhere anytime soon. Mass-wise, 71% hydrogen, 27% helium. All these other elements are what we are made of, and they all exist in the sun. And I have no idea what's causing it. It's just the way it is. Yeah, solar wind is possible. 67 elements have been detected in the solar spectrum. Side note, the solar spectrum spectroscopy was originally done by a Catholic priest about 100 years ago or so. So this all, there's so many ties. You know, I was raised Catholic, and my mother, you know, she's dead now, but she would really have a problem with my hobby because in one respect it goes against what she taught me to believe, et cetera, et cetera. In the other respect, I believe it just clarifies the whole thing to me. So I try not to get into all that, but I'm very spiritual when it comes to astronomy, and especially the sun. To me, that is my religion. Inside the sun, now this is all conjecture, because of course nobody's traveled through the sun. You have the core, where all the action takes place, hydrogen fusing into helium, releasing gamma rays and photons. Okay. Then you have what they call a radiation zone. Now the only interesting part here, the only part of the sun where hydrogen fusion takes place is right in the middle of the core. And this is still a plasma, but it's a gas actually. It's such a dense gas. I mean, it's way denser than lead or rock or anything we know of, but it's so hot and so pressurized that it still has the characteristics of an ionized gas, which is what they call plasma. So, I mean, the density is unimaginable for us. You know the old teaspoon weighs a billion tons thing they always see on TV? Well, a teaspoon of that would surely weigh a lot. When the energy is released, it goes through this radiative zone where it cools, and there's no fusion going on in here. This is all just cooling off of stuff. The random walk pattern, they call it, where the photon takes forever to get from here to the outside so you can see it. In the convective zone, the stuff is losing its heat. I'm trying to make this as simple as possible because we're all not scientists. There are some scientists here, and I apologize, but I'm not one of them. Second tier supergranules, third tier granules. Then you get to the stuff you can see through my telescopes, the photosphere and the chromosphere. The chromosphere is where images like these are taken, and this is H alpha wavelength of hydrogen fusion light. And that's what we look at through these cool Coronado telescopes. The photosphere is what you're looking at through your telescope with a white light filter on it. Okay, and these are both areas where these photons are finally released into the corona of the sun. And it's very cool compared to the core of the sun. So that's kind of the, okay, who can tell me all about this right now? Can I get 6 volunteers? I'll make it quick. Oh, I know you two are obviously going to volunteer. So, everybody practice turning on and off their flashlight. And what we're going to do is create our own little chamber of nuclear fusion inside of here. Oh, you want to write? That's where you, okay.